chapter 7.4, which will conclude chapter 7. We're going back to estimating mu, but now we're estimating mu1 minus mu2. Now the reason for the sub 1 and the sub 2 is now we have two populations where before we only had one. So there are two different types of samples that we'll look at. Independent samples and dependent samples. Now, independent means of your two populations, the samples that you draw from them have no correlation. They're not related in any way, completely unrelated. They're just two different samples. Where in dependent samples, each value in one sample can be paired with the corresponding data value in the other sample. So when I draw a sample from mu1, it is related to that same or a value in mu2. Now, for our purposes, we will only be our discussion or limit our discussion to independent samples. I wanted to explain to you dependent, but all we have to worry about are independent samples. So, again, we don't know the population mean, which means that we will be looking at x bar 1 and x bar 2 instead of just x bar. So here I've given you the mean and the standard deviation, but down here is what we really need to get to and for you to really be able to do your calculations. Now again, since we're estimating mu, just like in 7.1 and 7.2, what is significant to recognize is when sigma is given, because then we use z sub c, and when sigma is unknown, we use t sub c. So we're first going to look at examples or the formulas when sigma is known. So notice it's z sub c, and now my margin of error formula is times the square root of, this is sigma 1 squared over n1 plus sigma 2 squared over n2. And then notice how the confidence interval changes. It was x bar minus e, but now we have two x bars. So it's x bar 1 minus x bar 2 minus e, and it's x bar 1 minus x bar 2 plus e. So be careful, don't put a plus here because it's on the plus e side. You still take x bar 1 minus x bar 2. And we are estimating the difference of the mu's. So before we actually do an example, I want to talk about the importance of estimating the difference, because here's what is of importance. When you subtract two values and you only get a positive calculation, that tells us that mu1 has to be the bigger number, because a bigger number minus a smaller number always yields a positive number. So in your confidence interval, if you calculate two positive values, then you know mu1 or population 1 has a larger mean than population 2. If your calculations in your confidence interval give you two negative values, well, the only way to subtract numbers and get a negative number is if the first number is smaller. So that tells us that mu1 is smaller, or if you want to look at that as mu2 is bigger. So when you calculate in your confidence interval two negative numbers, then you know the population mean of the second population is a bigger mean than the first population. And then the other scenario that can occur is when you subtract and one of your values is negative, which when it's negative, that means mu2 is bigger. And then when it's positive, it means mu1 is bigger. So in essence, there is no significant difference, because sometimes the average in mu1 is larger, sometimes the average in mu2 is larger. So let's just apply this. This is where I think you'll actually see what's going on here. Okay, it says, which battery lasts longer? So we have two populations. We have Duracell, which is population 1. It gives a sample size of 42. Its sample mean is 9.8. And notice sigma is known. That is important because we know now we'll use Z sub C. Energizer is population 2, so my second sample size is 38. Its sample mean is 8.1, and again, sigma is known, 3.5 hours. So, since sigma is known, we know we use Z sub C. This reads, Find the confidence interval for the population difference of lifetimes for these batteries. Okay, so Z sub C is what we use, 90%. So I'm going to use this small table. Here's 90%. So Z sub C is 1.645. So, find my pen. I know this is 1.645. Now, here's the formula for my margin of error. It's Z sub C, 1.645, times the square root of sigma 1, so 2.2 squared, don't forget to square it, divided by N1, 42, plus sigma 2 squared, 3.5 squared, divided by N2, 38. Now, in your calculator, here's the only place that you need parentheses. So let me see if I can show you on the calculator how to do this. So 1.645 times the square root is second x squared. Mine automatically opens up a parentheses. If yours doesn't, be sure and do so. Then you're going to push on your calculator 2.2 x squared. Don't close the parenthesis, just go ahead and put divided by 42 plus 3.5 x squared divided by 38. Now close your parenthesis and push equals. And you get 1.088 or 1.09. Again, in your calculator, it's 1.645 times the square root of, open parentheses, 2.2 squared divided by 42 plus 3.5 squared divided by 38, close parentheses, then push equals. Then my confidence interval, and this is where you need to be careful because we have two populations, so it's x bar 1, 9.8 minus x bar 2, 8.1 minus the margin of error, and we are estimating the difference of mu1 minus mu2, and then we have x bar 1, 9.8 minus x bar 2, 8.1 plus the margin of error. So I'm going to calculate those using my calculator. And on the left side, I get 0.61. But what I'm really interested in is knowing that this is a positive number. Then on the calculation over here, I calculate 2.79. But again, what I'm interested in is knowing that it's a positive number. Because if I get two positive numbers, then that tells me that anytime I subtract these, I always get a positive value, which tells me that mu1 is larger. So now I know that mu1, which is Duracell, is larger. So in my conclusion, I would state I am 90% confident the average lifetime of a Duracell is longer than Energizer because Duracell was mu1 and it is a bigger number, so it lasts longer. Now, that is an example when sigma is known, so we use Z sub C. So now we need to look at an example when sigma is unknown, because now when sigma is unknown, we have T sub C, and we will use the student's T distribution. So that's where we have to be careful. So notice the margin of error is basically the same formula, other than this is T sub C, and instead of sigma, it has S. Now we have two sample sizes, so on our student's T distribution, we have to have a DF. We'll always use the smaller sample size, -1. And then the confidence interval is calculated the exact same way as we did the last problem. So the only difference is your student's t-distribution instead of the z-table. So let's look at this example, and that will complete this section. Assume absorption times are normally distributed. Find a 90% confidence interval for the difference in average absorption time for the two drugs. Okay, so what we have is Tylenol, so that's my population 1. Sample size of 8, X bar of 24, S, so right here, sigma is unknown. So sigma is unknown, we know we're going to use the student's t-distribution. The second population is Advil. Notice my sample sizes are different, and here is its mean and its standard deviation. So, since sigma is unknown, I'm going to use T sub C. Well, I need the DF, and this is where it comes in. DF is N minus 1. Well, I have two different sizes of N. So always use the smaller one minus 1. So I'm going to do 8 minus 1, which is 7. So I'm going to use 7 on my student's t-distribution, and 90% would be 0.900. So my DF is 7, which is right here. 0.900 is right here, which is 1, 2, 3, 4, the fifth block over. 1, 2, 3, 4, 5, and that is 1.895. So in my margin of error, it is 1.895 times the square root of, shake my pen so the ink will come out, it is S1 squared, 3 squared, divided by N1, 8, plus S2 is 4.9, so it would be 4.9 squared, divided by N2, which is 10. And again, in your calculator, the only place you need parentheses are here and here. So when you put that in your calculator, you will get 3.56. So now we can create the confidence interval, which is X bar 1, 24 minus X bar 2, 29, minus 3.56. And we're estimating the difference of mu1 minus mu2. X bar 1, 24 minus X bar 2, 29, plus the margin of error, 3.56. And when you do that calculation, you get 24 minus 29 minus 3.56, and you calculate negative 8.56. So what I'm interested in knowing is that's a negative number. That's what's important. Over here, I'm going to get 24 minus 29 plus 3.56. Sorry, my calculator, I was hitting a wrong number. There we go, negative 1.44. And that's negative as well. So when we subtract numbers, so we want to know the estimation of subtracting this, what I do know is that they are both negative, and if they're both negative, that tells me that mu1 is smaller, or you could have said mu2 is larger. Now we're talking about absorption time. So mu1 is Tylenol, it's a smaller number. It takes less time for Tylenol to absorb than Advil. So my conclusion would be I am 90% confident the average absorption time for Tylenol is smaller or faster than Advil. That concludes 7.4.